what we're going to do here is take the derivative of ln of x. There are maybe half a dozen completely different ways of taking the derivative of ln of x. I'm going to use a technique here that we're going to be using a lot. So first we're just going to write down, hey, we're going to try to take the derivative of the ln of x. So ln of x, like that. And the technique goes like this. If you want to take the derivative of something you don't know, try writing down y equals. Now remember, by the way, the goal is to find y prime at this point. Now why do I do that? So I have an equation that I can do something both sides to. What I'm going to do is take e to both sides. I'm going to write down e to the y equals e to the ln of x. Well, that's just x. Now remember, the goal at this point is to find y prime. Well, what I'm going to do is take the derivative with respect to x of both sides. So derivative with respect to x of both sides. They're both functions. Their derivative would be the same. The easy side is the right-hand side. That's just 1. Not a big deal. How am I supposed to take the derivative of the left-hand side? Ready? That's e to the blob. Right? The blob is ln of x, but I'm not going to worry about that at the moment. The derivative of e to the blob is e to the blob, like that, times the derivative of the blob. Well, I don't know what the derivative of the blob is. I can certainly write down the derivative of the blob. And you see what we have right here. We now have an equation that has y prime in it, and we can just solve for y prime. So what we're going to get is that y prime is equal to 1 over e to the y, like that. That is a correct answer. However, you notice my original function didn't have a y in it, and my new answer does. This is bad. But we go to this box right here, and we see that e to the y is x. So we see that the derivative of the ln of x is just 1 over x. We can get that from the picture, we can get that from the definition, we can get that from the chain rule. It's just and a composite function a different way. But for the moment, let's just remember that the derivative of ln of x equals 1 over x. We certainly don't have to go through this process every time we want to use it. However, I just want to put one example here, showing you what we might have to do when we take a derivative involving it, right? So, for example, if I have the cosine of the ln of, what can we do here? How about x squared plus 1? We'll do it like that. Now, what I see is an outside function, outside function, outside function. So I see cosine blob. The derivative of cosine blob is minus sine blob. Oops. My blob is the ln of x squared plus 1. Now what I see here is the ln of blob. Well, we just found out the derivative of the ln of blob is 1 over blob, like that. And my blob keeps getting smaller. This is now my blob. And I now need to multiply by the derivative of that, but the derivative of that is just 2x, and we're all done. So when you use the derivative of the ln, you don't have to derive it every time. We can just remember that the derivative ln of x is 1 over x, or the derivative of the ln of blob is 1 over blob times the derivative of the blob.